Let's do some math for fun. And here I have this question for you guys. We are going to find the value of b so that the graphs of b to the x and x, they will only intercept one time. And before I show you guys how to do this question, let me tell you guys about the story behind this question. When I was a student at university, there was one time that the professor was going over about b to the x and x. And he said that the exponential can never intercept x. And I was wondering, I don't think that's right, because I can tell you an example like right here, right? Let's look at, okay, this is y is equal to x, which it needs no introduction. But if you choose the base b to be 1.0 something or 1.01, for example, you're going to get a really flat exponential graph. So it's going to be like this. This point here is still going to be 0, 1, because when x is equal to 0, 1.01, for example, to a 0th power, it still get 1, right? This is going to be really flat, and then it's going to be touching this for sure. This is the graph for b to the x, okay? So I show the professor an example, and then, yeah, they do intercept. Well, the situation that he was thinking is that we don't normally look at b to the x if x is like a small number, like 1.001 or something like that. Usually, we look at b as a bigger number, such as e, right? We look at e to the x a lot. For example, if you look at e to the x and x, e to the x will look like this, right? This is the exponential graph, touches, this is 0, 1, and then it's going to go up. And then y is equal to x is still this right here. And in this case, of course, they will not intercept. If you look at this is e to the x, for example, right? So now the question is there any value for b so that b to the x and x, they will just intercept at one point? So this is the question that we were trying to answer, right? So let me just draw this for you guys. This is an arrow, and this is y is equal to x. I'm trying to find some b value so that y is equal to b to the x. Once again, that's still an exponential graph. It's going to touch the y is equal to x exactly at one point. And as you know, this is going to be increasing, right? Because that's just the exponential graph. It's always increasing. Likewise, y is equal to x is always increasing as well. This is going to go up, and it will never go back down. So once they touch one time, they can never touch each other again, right? So anyway, I remember that time, I just raised my hand like this and tell the professor with that example. And then after that, he realized, yeah, we were right. I was right. And he wanted us to solve something like this. Anyway, pause the video and give this a try first. Okay, so hopefully you guys all have a chance to try it, and leave a comment down below and let us know what your answer is, or maybe what your approach is, okay? Okay, so this is how I'm going to show you. First of all, we are considering these two graphs, right? And let me just put it down right here. First one is y is equal to b to the x. The second one is y is equal to x, okay? And in order for them to intercept each other, of course, at this point, they must have the same x and same y value, the same point of intersection, right? So we must have, let me just write this down. We must have these two together, right? In the sense that, okay, this is y, so we must have b to the x equals to x. So let me just write this down. And I'm working with this equation. It has two unknowns, namely the b, namely the x, right? But if you look at this, I just have two unknowns. If you look at the original, you have three. X, y, and b. So this is the first condition that we have. And let me just label that right here. We must have the same point at this point, right? Same x and y coordinates. And now, what else do we have though? Because we have two unknowns, we must have another equation in order for us to solve two equations with two unknowns, right? Well, right here. And this is the calculus part. If you look at this point, the derivative at this point on the red curve, it must be 1. The derivative right here, right? Because when they touch exactly at this point, the curve touches exactly at this line, right? This line happens to be exactly the tangent line for this graph, isn't it? So in another word, I have to look at the corresponding derivatives. So right here, I can tell you y prime differentiate b to the x, we get still b to the x, but we multiply by ln b. This is how we differentiate when b is not e, right? And we differentiate that, we have y prime is equal to 1. So the second condition that we must have is that at this point, the derivative of the red curve and the derivative of the black line, they must be the same. Namely, we must have b to the x times ln b is equal to 1, like this, okay? And now this is what I'm going to do with you guys. We see that b to the x is equal to x, so I can just replace this x right here, right? This is b to the x, so we have x times ln b is equal to 1, like that. No problem, isn't it? B to the x is x, b to the x is x. So if you look at this right here, I need to figure out what's ln b though. Or maybe I need to figure out what's x in terms of b. Let's look back to this again. I will change this to blue and red. I want to come up with ln b and I have to make the connection. Let me just look at this. Let me write it down again. B to the x is equal to x. Let's take ln on both sides. And once we do that, you see I can take the x to the front. So we have x times ln b. This is equal to ln x, isn't it? I want to get ln b in terms of x. So right here, I can just divide x on both sides. Namely, I get ln b is equal to ln x over that x, right? So you see this is the x that we had earlier because that was b to the x. And for ln b, which I can replace that with ln x, I want to put this down in blue, ln x over that x. And of course, this is still equal to 1. So this is kind of like a special way to solve system of equations, isn't it? And another special way to do substitution. Now, I have just one equation with one unknown, and you see it's pretty nice because the x and x will be cancelled, and you see we have ln x is equal to 1. And now you can just do e to this, e to that. So in other words, x is equal to e. Wow, this is how special e is. It happens pretty much a lot of places, right? Okay, x is equal to e, but I want to find out what b is. So I can just come back to here, plugging e into this x and that x, right? You can also plug in x equal to e right here, but I think it will be easier if you plug in e into this x and that x. It's easier. So let me just go back to my first condition. X is equal to e, so we must have b to the e's power. It must be e. And now what? I want to solve for b, and this is just a number in the power now. All I have to do is I can just go ahead and do it. Let me just put this down in blue. Raise both sides to the 1 over e's power. Can I do that? Yeah, so that e and the 1 over e power, they will cancel each other out. In another word, we get b is equal to e to the 1 over e's power. How cool is this? And now, as you can see on the screen, when the base is equal to e to the 1 over e, the exponential graph, it does intercept the graph of y is equal to x at exactly one place. This is so cool, isn't it?